Today, we are presenting the Explainable AI Handbook, a framework for defining and comparing all kinds of methods in the field of XAI. It is well known that machine learning models are being used in more and more high-stakes scenarios. However, in these scenarios, we require the decision process to stay open to scrutiny and further evaluation, even when the decision itself is the correct one. In other words, we need the decision to be both correct and to be taken based on the right criteria. This constraint is vital, as it prevents unintended biases to endanger those affected by the model's decision. Furthermore, scientific advances can also accelerate with a deeper understanding of the features and properties that drive modern ML models. Unfortunately, contributions on the field of XAI seem to follow vastly different and often self-defined standards of what constitutes an explanation or what counts as an interpretable model in the context of machine learning. So, if we are all working on different problems, how can we know if we're making progress? How can we possibly agree on a standard for critical systems to comply with? We propose a framework that gives us the ability to contextualize contributions in the field of XAI. This framework is designed to be general, so that most existing contributions in the field can fit under the vocabulary of this framework. And yet, it provides a set of well-defined primitives that allows different contributions in XAI to be compared to one another. This is how the framework works. We start by thinking, how do we normally solve a task with ML in relation to how do we solve a task in general? This way, we can compare our expectations regarding the properties that a model has. Let's think about a simple classification task where the high-level objective is the classification of all pictures showing a chicken. This goal is then represented as a set of low-level mathematical primitives and operations that ultimately generate some kind of output that we can read back and judge whether the initial goal has been reached or not. So far, nothing out of the ordinary, but what we often forget is that while translating the abstract goal into formal language, we have oversimplified the initial task. For example, we expect that the features most representative of the chicken are detected in the area that shows the chicken and not in the background. However, the definition of the model does not guarantee that this property will hold at all. In our framework, we represent all these latent properties as non-functional requirements. That is, all constraints that the algorithm is expected to model even without them being explicitly defined. Finding evidence that the model complies with these non-functional requirements is exactly what creates the need for explanations. So, what is an explanation? Well, in its most general form, an explanation is a process by which we can describe properties about other things. In the context of machine learning, we are interested in describing non-functional requirements that the main model is supposed to comply with. Now, to prevent any kind of circular definitions, we require the input of explanations to consist only of facts, meaning anything whose existence is unambiguously true. These facts are usually found among the same mathematical primitives that define the model itself. For example, the weights of a neural network, the training samples, or the value of the loss function after training. Note that in the framework, we call this process of explaining an explanation. The input to an explanation is then called an explanandum, and its output is referred to as an explanans. Alright, so far, when going from high to low-level representations, we rely on a formal definition. Let's now have a look at the other end, going from the low-level to the high-level domain. Let's say we just obtained the prediction of the model with respect to a sample in the form of a vector. For classification tasks, we usually look at the index of the prediction with the highest value, and we just consider the class that was previously assigned to that index to be considered as the predicted class. So, if the class chicken was assigned the index 2, and the highest value of the output vector happens to be 2, we consider the prediction to be correct. This kind of arrangement defines a mapping from the low-level formal primitives back to the high-level domain. We say that we have assigned meaning to the output of the model. This meaning is tied to the high-level definition of the task, and when the meaning is coming from an explanation, we effectively expand our understanding of the model and its non-functional requirements. When looking at textbook definitions of the word interpretation, this is almost exactly what we find, so we can coin this term as an assignment of meaning. Now, it would be impossible to talk about high-level tasks without the involvement of human actors. The process of defining a task, its formal definition, and the implementation of the model's output is highly dependent on who the consumer of the model's output is. A domain expert, like a doctor, can condition the numeric results with their medical knowledge. A machine learning expert can include notions of the training process to estimate how certain the prediction really is. Or a layman might just need to be shown the textual representation of the predicted class. In general, we say that the interpretation of the model's output, or the explanans, is conditioned by the mental model of the consumer, or the explainee, as we call it in our framework. And there you have it, a framework that defines what is an explanation and what is interpretation. Let's now see how to use it. As mentioned earlier, this framework enables the comparison of different contributions in the field of XAI that at first sight might not even be comparable. And here's how. Suppose that we have a model and there are two available methods that fall into the umbrella of explainability. Let's say we have GradCam and Kernel SHAP, for example. According to the framework, these are explanations, and their implementation unambiguously define how they work. However, we can still ask what is the input and the output of GradCam. We know that GradCam receives a sample and a pre-trained model, and that the output is a one-channel representation of spatial importance. But how is this importance defined exactly? We're now asking about the interpretation of the explanans of GradCam. In short, by using our proposed framework, we can locate what components from either method fit where within the framework. We can repeat the same process with the elements and definitions of Kernel SHAP, and then compare their explanandum, their explanans, their interpretations, etc. Even more importantly, we can establish if there are any elements of the framework that are not well defined by the explanation, or if its interpretation is somehow vague. No matter what the explanation claims to do or how it achieves it, our framework provides enough structure to sort and compare methods from their conception to their end results. So, what's missing in order to advance the field of XAI? After going through some of the most popular methods associated with explainability, we want to highlight 3 patterns that future work should focus on the most. First, before working on the specifics of an explanation, explicitly define the non-functional requirements that a task should fulfill, and that the explanation itself will be proving. This can be achieved by defining a better hypothesis, for example, one that can be falsified. Second, proponents of XAI methods should be careful when addressing the complete scope of our proposed framework. In particular, a clear interpretation should be provided. Third, define metrics to evaluate the results of explanations, similar to how we compute accuracy on an image classifier, even though this is not the objective that is being optimized for. Similarly, we should think about metrics to compare other components in the framework, like explanandums and explanans. Thank you for watching. Don't forget to check out the full paper where we have more details regarding all definitions and examples of how to compare two or more XAI methods together. In the name of my co-authors and myself, I look forward to discussing with you and advancing further the field of explainable AI.